Okay. Now that's our webinar run, and it all started on March 9. That's about when I taught my first course at Cisco. And a few interesting things happened there when I taught it, which I will tell you, plus that meeting, which I will also tell you about. But let's go here. That's today. April 28th is today. And that's what I have for you today. That's my plan. So we will try. We will talk about positioning. We'll talk about the news in quantum computing. It must be that you're enthusiast of that, because as we said last few times, still today there is no application that will be at what's called quantum advantage, something that you can do on a quantum computer, but cannot do on a regular one. So there is no such application so far. Even though some medical companies like the Cleveland Medical Research Center, which happens to be the largest and the most important research center for medicine, bought their own computer. So they have their own computer. I don't understand why they don't use the cloud ones, but that's not yet practical. They just say, oh, we think we will do this when it comes to this. So far, that's where it is. Yesterday, I heard one of the Qiskit talks, and they said, so far we can factor using Shor's algorithm, we can factor 15. That's the largest number that so far has been factored on the quantum computing. And they got 3 and 5, as you would expect. 3 times 5 is 15. And then the estimate of how many qubits they need. Now, the number of qubits that you need is not so easy, because that all depends upon the noise. And therefore, the research actively works on both sides. They work on how many qubits I can get, and then how much noise. You can estimate it yourself. In other words, having 1 qubit, you can represent all numbers between 0 and 1. And having 2 qubits, you can do up to 4. And having 3 qubits, you can do up to 8. So if you're talking about numbers that are represented by 500 digits in digital, you're talking about, let's not just talk, but let us draw a picture so that we can relate, right? So if we're talking about a number that is here 500 digits, then such a number will have number that's significant, that's close to breaking RSA encryption. That will be, well, 10 to the power 500. 10 to the power of 500. Well, look like a big number, because in the whole universe, you only have 10 to the power of 90 or 92 particles. So the usual argument is that, guys, even if you had the computer big as a universe, you would still not be able to compute it. But that's not true, because instead you have a computer that is a quantum computer, and each bit, each qubit, can represent either 1 or 2 or be in any position in between. And therefore, all you need is as many qubits. Let's put this in number q, as it takes to represent this number. And that is 2 to the power of q. So let's put it here. That's a very, very rough estimate, an amateur estimate. But if you have as many qubits as would equal 10 to the power of 500, then seemingly you're good. Now, how many few do you mean? Well, just convert 10, and instead of 10, write 2 to the power of 3. In other words, move that little thingy and say this is equal to 8 is 2 to the power of 3. That's my way of representing 2 to the power of 3. So we're talking about 2 to the power of, multiply this, 1500. Therefore, approximately, you need 1500 qubits. That's all. And how many qubits does today's computer have? Anybody knows? Let me bring up the chat and see if anybody says. How many qubits do we have? 443. Okay, Aisha, it's 443. And that's the Osprey computer. Well, and we were at 127 just maybe 2 years ago. So it seems that give it a year or two. Now, the real truth is that this may speed up, that development may speed up, or it may slow down, that we don't know. And you may need more, because you need many more qubits so that noise is eliminated or neutralized. But that's approximately what we're looking at, which means that, you know, in a couple of years, it may be possible. Unless some secret entity already working on that, and they already have much more power and they are reading all the RSA signatures. But I think that's not very likely, because you need huge labs and you need IBM kind of size. And then if I were a secret agency, I would probably ask IBM to do it for me. So that's an introduction to what we're going to talk about. If we agree with this, and I already showed you the three very funny answers from the experts on Qiskit. And by the way, anybody here who wants to become a Qiskit advocate, I'll tell you what it is. Just spell it like this. That's, oh no, not the musket, but Q-U-S-T. With all the technology, I type slow. Qiskit and is anybody interested in that? Then I can tell you what it involves. Okay, what is involved, says Aisha. You need to find that place where they accept Qiskit advocates and put it on your calendar, because they only open this enrollment once a year in June. But in June, you can try. What is involved is, first of all, passing the Qiskit developer exam certification. But I looked at it, it seems reasonable. It's not all that hard. And now that I'm talking about this, I'm kind of putting myself in the position that I have to do it. But that's my way of life. I'm asking somebody if he's interested in me teaching that, and then I have to learn about this. So I do plan to do this. I think it is fun, even though it's not bringing any money right now, but we all agree, we all here agree that it is fun. Okay, so in June, you apply, you also pass the certification, and then you talk about your interest. That's what I imagine. I'm not sure exactly if there is an interview. There are about 2,000 Qiskit advocates right now from all walks of life. And just now, I came to you after a conversation that I had with another guy. Let me show you this other guy, because that was totally accidental. If you go to LinkedIn, okay, and if you remind me of the name of the guy that I just spoke to. No, but we have to open the calendar and his name will be there. Philip Nikolaev, an interesting person, but I'll show you what is interesting to us. Oh, yeah. Philip. Can't believe it. It should be one connection. So he is an enthusiast of quantum computing. That's why I mentioned that. But he's a poet, and he grew up bilingual English and Russian, and he got an enormous number of all kinds of degrees. And now he is into marketing. So that's not a random fact that I'm telling you. That's an interesting thing. I'll ask him about if he wants to be, or if he is maybe a quantum or Qiskit advocate. Okay, so let's go back and let's try to cover what I promised we will cover here. We said that we are talking about new positioning for QC for the masses. And even though I didn't say so, but I'm really leading up to what we've done so far, we get the picture. I think that's an easy picture that tells you most of the things. First of all, it is in the future. So as I told you at the first training, I got 10 people. 8 of them filled out the feedback. 6 or 5 were all 5s. That's a needed course, and that was great, and please do it again. But 2 of them said 2. No reason, we don't know why, but I mentioned that, look, you call it quantum computing for classical programmers, and you would think that means that you can learn another language like Python for Java programmers. But that is not the case at all. It's an introduction to the future, an introduction to this amazing area of quantum physics and quantum computing and what it can do for you, let's say for a company in the future, but not right now. So I mentioned that those people who are very practically oriented and who came to the training and they discovered that it's misleading title. So therefore, I'm changing it. I'm suggesting to the company that let's change the outline, let's change the description of it, and let's describe things as they stand. That is a new positioning of QC. And that's why I was talking to Philip Nikolaev, because he is in marketing of all things, and he is in QC of all things. But yes, we agree that it would be an interesting thing, to change it. Now I'll tell you a little bit of what happened, and then I'll do the lab so that we also advance in this area. So what happened is that exactly on the day of our course, April 11, they came up a little note on IBM website, which said we are changing, we're switching over to a new environment and a new execution engine and the new format. And it was up and down on the 11th and the 12th, exactly when we were having our course. So when we were doing the lab, and that's what I want to offer you, the first such lab, then we could not rely on IBM to run. So instead, we had to rely on our own environment. So I brought up the virtual machines, and that worked great, but somebody had updated the libraries on the Qiskit part, and now it was deprecated and not quite working. So that is the little sorrows of a trainer, of a Qiskit trainer. By now, we have this. My labs are still here, and I am updating them to the latest version of the library so that this one really works, but also they report that IBM has fixed everything and that you can run their labs. That's what I suggest for us today. Let's go to IBM Labs. Let's look at the later version of them, and let's get the benefit of, first of all, running this lab, and secondly, verifying how well it runs. Okay, if everybody's okay with that, and keep in mind that you need to speak up because I do not see your chat. So keeping that in mind, we go here and we search for it. Now, of course, we can't avoid using ChatGPT. It's right here. And they also changed things. It should come by default as latest version 4, but they changed the default at 3.5. We choose the right one. And instead of searching, we can say, where is the IBM Qiskit tutorial? That's an interesting story about ChatGPT, and I just finished teaching that yesterday. So by now, I'm using that with full right. And by the way, you probably get the same if you use Google. If you use Google, and you have to be in Edge, of course, and on Bing, of course, but then supposedly it allows you to talk to ChatGPT that way. Now, there are many opinions. One of them says that it is just a marketing engine for Microsoft and that don't use it because it's all too polite. It's not exactly ChatGPT version. And I think everybody would agree that ChatGPT is the real standard to go to. Whether it is exactly the same thing that you get on Microsoft or no, is immaterial. We agree that if you are looking to get to ChatGPT and asking yourself, well, does Microsoft give that to me? Then on this level, you go back to ChatGPT. It's only when you're integrating your application, then you're asking yourself what versions. And it told me right away, right here. So let's look at that. No, it just, oh, maybe it was the right thing. So let's try. Yes. Well, that's GitHub. No, where's the documentation? Right here. And that documentation is new and it has a version and it says 042. That's interesting. They didn't tell you what version it was. So what we want to do is get started. And where are your documents? You know, I know I'm doing a dangerous thing by never having tried this in real life, but there must be tutorials. And in tutorials, there must be basics. And that is the lab. So it was generated from this. What is this? Okay, it was from that, but what we're interested in is back. That should work. So for our pleasure, we can run it here, verify how good it is now. If I ever get to teach it again, I will still use my own controlled version, but that should tell you that's what it is about and allow you to run it here. So let's do it. I suggest that we do it here together, and that's talking about circuit basics. So what are those circuits? It's exactly how you connect your qubits. So if you have an quantum computer, Osprey, IBM Osprey. Then show me a picture. That's about what it looks like. And all this gold is just on the outside. But these are connections between qubits. All qubits are fully connected. You can connect each qubit to another. And that's what you build now. Inside of that, you can form a circuit that will first of all describe the qubits where they are. So that right away tells you, if you haven't ever tried it, it tells you how you write the computer program for the quantum computer. You first build this computer. Now, to build it, you need to import NumPy. Well, that's probably for later computations, but you need Qiskit, and from there you import quantum circuit. Now, somewhere there must be a place to run, and that's what I do not see. So I'm mildly surprised, but I don't see where you run it. In any case, they tell you what will happen when you run it. So what if I cannot click? I get a promise that that's what will happen. So in this case, I'm building a little circuit with 3 qubits. Building a little circuit with 3 qubits, then they go into theory of what that is. So they tell you 3 qubits, each one can be in a 0, and it can be in 1 position, and can be anywhere in between until you look at it. So I can never stop being fascinated by the whole idea, which is expressed in these lines. It says you have 3 qubits, but they can be not like bits, not 0 and 1, but anywhere in between until you look at them. Then you allow them to do the calculations according to the rules that you will tell, and then you come back and look for the answer. Why is there this square root? That's because all probabilities should come up to 1, and that would be a bit more, so you need to divide by the square root of 2. I'm not going exactly into all of the details of calculations, but giving you only the general idea here. The next step is, okay, what do you do with them? And remember, I'm looking at that for the first time. So what you do with them is you're telling it my circuit, and that was called circ here. So here is the very first qubit here. What we want to do with this qubit is to make it really a qubit, because it starts by default with a value of 0. That is what you would expect. Every qubit initializes to 0. But then you want to make it a real qubit, which is oscillating somewhere between 0 and 1 until you look at it. The way to do it is to say this letter H. H stands for Hadamard, Hadamard gate. It's spelled in French Hadamard, but in English, some people pronounce it as Hadamard and some people as Hadamard. And there is also a D at the end, I believe. D at the end. So it is an Hadamard gate. I will still pronounce it Hadamard. So That's what Hadamard gate does. And now there's the explanation and accordingly the pictures. But we, at least so much we can say is that, okay, I had the qubit in the 0 position, and now I'm multiplying its probabilities so that it's not 0. I take the bit number 0 and I'm multiplying the probabilities to put into what is called superposition state. It now can be anything. That's as far as qubit number 0. Next is qubit number, well, the same qubit, but now I want to do this. I want to do a C0 on qubit 0, and I want to put the result into the target qubit 1. So if I do this C0, this is controlled NOT, and it works based on the 2 inputs. First input is the control qubit, and second one is the target qubit. Now, if you're worried that you're overwriting your results, then indeed you are. But if you don't want to overwrite your results, you can say, but put the output somewhere else. But what we're doing is we're taking the first qubit and doing a controlled NOT or C0 on that, so that qubit 0 will stay where it was, and qubit 1 now will be in a Bell state. And that is making them connected. It is making them related to each other. That's the famous, what do you call it? Could you remind me how you call it? Let me go to chat. I mean, what is involved is a good question, but I mean, what is the Bell state? What do you do to your 2 qubits to put them in the Bell state? The answer, you entangle them. Yes, you put them in the entangled state. All right, so now these 2 qubits are connected, and whatever happens to one happens to the other. And that is the famous part of the quantum physics and quantum computing. That's how many algorithms work. I'm surprised, between you and me, I'm surprised that they start the circuit basics right away from, okay, Hadamard gate, which is not the first one, and immediately put them into the Bell state. But at least that's what they do. So let's look at what they do now. They add another C0 gate on the first input is still the same. It's a control qubit 0, and the output now is in 2. That way, you have 3 qubits working for you. Put in the qubit in some GHZ state, and I don't know what it is even. But in the end, you can draw whatever you created. That is, you are building your computer. So you're taking the first qubit, qubit 0, putting in Hadamard gate on that and making it in a superposition. So one way to represent it is with the sphere. It's just too many names to remember. One, two, qubit here, Bloch sphere. That's what it looks like. That is a qubit, which is not at 0 and not at 1, but it's somewhere in between, and that's what it looks like. So it is a bunch of probabilities, in this case, just 2. A bunch of probabilities that are pointing somewhere, not to a definite 0 and not to a different definite 1, but it is in the superposition. So going back here, that is the Hadamard gate, and I take the first one and make it a Hadamard superposition. Then I take that one and do a CX. That's the second thing that happens. So the second line corresponds to this. I'm still building my computer. In other words, I'm building the circuit. And then I'm doing this interesting thing. That is still my control bit. But I'm also putting another bit in this belt state. Except here they are saying it's GHZ state, somewhat different. So let's look at what do they mean and what is it that they're building. They say we can visualize our circuit using Qiskit draw. That would really work if you were in an environment that understands what you are doing in the Python, in a Jupyter notebook, which plots the circuit in the form that is found in many textbooks. Yes, guys, I really need to figure out what's the new format of the tutorial, and that I will do. So now they explain this. In this circuit, the qubits are put in order. This is this order, 1, 2, 3, and this is the order of what happens. This thing happens first, this thing happens next, and this things happen after. That's done sequentially. It's not done all at the same time. The qubits are put in order, the qubit 0 at the top and the other qubits at the bottom. We see that the circuit is read left to right, as I told you, meaning that gates that I applied earlier in the circuit show up further to the left, right here. And as we said, it is sequentially executed. And now comes the confusion part. So now that we represent the state by a matrix, and for some reason they added one more row, well, that's the mathematics of that all. So I feel that I rely on you guys already knowing something. I obviously am not starting from the very beginning, and how many times can you start from the very beginning? That is not working in some situations. ChatGPT, for example, you can always start your talk from the very beginning and explain it. But quantum computing at a certain point, as you see, requires your knowledge. So therefore, I will ask you a question. Did anybody needed a reference? Was there anything, did anyone need a reference? In other words, was anything in what we discussed unclear because you didn't know it yet? And now that I'm showing that to you, you kind of get it, you grasp it, but some of the things remain either vague or unknown. No, nobody says anything. And so it was all very clear up until now. Then we can continue with the lab, which leads me to think that the next week, maybe we should do some more realistic lab. That's just reading the lab. In other words, next week will be different in the sense that it will not be improvised like this. There is certain advantage to doing this, but it will be more structured. So now what we're doing is we are calculating the state and then applying the circuit with the results, and then we want to draw it. Now this, what we're drawing is in the LaTeX format, and all we really did is create a little computer, create a little circuit with 3 qubits where we are going to do something. That was the first step. Now we want the sphere to show these qubits here and this position. This phase is a set of probabilities where they can be in any position. That is now back to quantum physics. Quantum physics tells you that you can never know the real truth, either because the real truth doesn't exist until you measure, or because the real truth is just probabilities. So there are different philosophical approaches, but that is amazing thing, that the amazing thing is that based on this philosophy, you have real computers. That's quite amazing. So it shows how this is represented. And then you can run on the Qiskit in the backend and see how they are executing that. And then you can also measure the results. So in this case, it seems that we measure 0, 1, and 2, but it doesn't say what the result is. It just says, I am going to measure these qubits, whatever their state is, and I'm going to put it into the regular qubit. So when you create a quantum circuit, first you say how many qubits there will be. And if you don't say anything else, there will be an equivalent number of regular bits. But here we're specific. We say I create a little computer of 3 qubits and 3 bits, which I will use to measure. And there he uses measure, but I expect probabilistic result, not 0, 1, but if you run it many times, you will get probabilistic results. So usually it is run many times. When you're saying, now I don't want to go and bother real computer. All I want to do is run a simulator, air simulator. By the way, I want to mention that air simulator, there is also probably an earth simulator and fire simulator. Just like in philosophies, there are 4 basic elements of creation. So here too, there are different simulators, air, earth, and so on. This is an air simulator that allows me to run this program without bothering the real computer. Now, if I were to run it on the real computer, nevertheless, I could. It would then go into a queue, stay in this queue for who knows how many hours, and get executed. And since it's very few qubits, it will be executed for free. So here we do the backend. We're saying that's how we're going to execute, job run, but I want to see the result. There you are. These are the results for me. It ran for probably 1,024 times, but usually how many times it runs, and returned probabilistic output. By running 1,000 times roughly, it'll get me a certain number of 111s and a certain number of 000. That is a perfect representation of the probabilities. And you see that there can be only 2 outcomes. Outcome 0 of zeros, and that's less likely. An outcome of all ones, and that is more likely. So that is the real output. Now, why there are no other outputs? Here we have only zeros, only ones. Meanwhile, our bits, they could be independently, they could be anything. Well, I'll tell you my guess, because you're not forthcoming with your guesses, because we put them into entangled state. We said, make them friends. That is the famous thing about bits, photons, or any other thing that is used to implement ions, to implement qubits, is that they can be very friendly, and whatever happens to one happens to another, and so they are not independent, but rather they are only this or that. I think that really is a great illustration of everything in quantum computing. One problem with that is that it's not practical. So what? But that's the ABC. That's what we need to learn first. Another problem is that, to my mind, that's very advanced. if we're talking about the first lab, then a lot of things have to be explained before. And that is even from the get started. But okay, that's what it was. Now, I accomplished what I wanted. I wanted to do one of the first labs here. We did it. I wanted to just discuss what is the new position of quantum computing, and I did it. And what I want to do later, next time, is discuss some news, because there are always interesting news. For example, can ChatGPT pass a QC certification? Well, that's what you will have to pass on your own. It gets pretty close. Last time they tried, it wasn't perfect, didn't get the cert, but it's moving there. That's one news. Another news is I think they are working on quantum computer that didn't have to work at super cool temperatures. That would make it very practical. I think photons is a good building material. And for photons, you don't need super cool temperature. For maybe electrons, you do. So that's what we will talk about, maybe. Let me put it here. Photons, qubits at room temperature, because that's how photons live. And GPT gets a kid developer certification. At least we can suggest that these will be the topics. And now I can stop sharing and ask you if you have any question. Now, maybe I'm not hearing you. But it seems okay. It seems that yes, all the camera is on and all of the mics are working. It's just that okay, we talked for 45 minutes and we didn't get any questions. So let me ask this. Any questions? Okay, great question. The recording will be published to YouTube and you will get an email with that recording. Another places where you can find it is by going to the webinar link. So let me show where that is. Okay, so if you go to Elephant Scale, and if you go to webinars there, right here, okay, then you see our webinar, it's right here. And it says, let's click on that. It says that all the recordings are found right here. In fact, I think we see all of them individually, one by one. That's the last one that we had. So it says 0421. And the next one will appear here. So I think this is correct. This is really the link. I'm clicking on it. And indeed, it was correct. So that's where you get it. Since you asked this question, what I can do is just give you that link. Let's go back to chat here. That's where you get all the links to all of the recordings, and our run. Our run is right here. So we go back to the browser, and our run file is here, and that's the latest news. We always put here everything that we do. So going back to chat. These are the two links that you need. All right, I going to have the ChatGPT next, right? So you're welcome there. But in any case, I'm saying goodbye and until next week. That's not a silly question, Milosh. It's like this. I read first the question. If I'm programming machine learning using Python, then how that would be different from quantum computing? So two approaches. Approach number one, I'll tell you the answer. Approach number two, ChatGPT will tell you the answer. So my answer is that it would use the same Python. It would use the same Jupyter notebook, let's say. So you're good on that part. You would need to go through understanding what are you writing now, just like in machine learning. You say something, but there is a lot of understanding behind. So you say model, you say weights, but you need to understand what you mean. So here too, you will be building a circuit, just as we described here. You will be putting the electrons into positions, and then you will be measuring the results. But of course, that's just what the code says. You will need to understand what it means. Now, I wonder, will ChatGPT agree to me? And you can speak to it in any language here, and you can start from anything. It will understand what you're talking about. I think it's a great answer. And probably we can say it points to one of the two theories. Is AI bad or is AI good? And if we say that it is good, then this answer says you will be partnering. So is it done? Okay, it's done. So I copy pasted this, and I suspect that if I just paste it, it will be all black. I don't like that. So therefore, I'll try to see if I can change that, make it whiter, and really put it on our file. That will be fun. Right here. That's all right. And say question. By GPT. And since I cannot even type, then it should fix all those errors. But it couldn't. Okay, that's the answer. And maybe we'll look at this question and answer next time. Okay, for now, I have to say goodbye and wish you all the best.